I'll show it to you. I'll do mornings, I will do everything differently.
No, of course, 40% my master's.
Okay, so let's get started. I think this is a rare privilege to have Prof. Hales give an overview of Flyspeck. I expect there'll be lots of useful things flying out of the Flyspeck project. So, this is one way to find out what we can mine out of it.
Okay, thanks for the invitation. I intend this to be an informal talk, so feel free to interrupt at any time with questions. Different people have different degrees of background about this project. Basic outline of the course. First of all, I'll give a few thanks and indicate what some of the general resources are for learning about this project, and then I'll give a brief overview of each of the major components of the project. So just to start with thanks and resources, I won't thank everybody by name, but the success of this project was really due to a large number of people collaborating in various ways. The best place to go for all the information about the project is just to our GitHub page. We've got all the proof scripts there, all the documentation there, and so forth. The article giving the proof was just published, or the formal proof was just published a little more than a month ago in the Form of Mathematics. And that's a rather short article, so it's not some big long thing describing 20 years of work. It's just less than 30 pages giving the highlights of the proof. So we tried to make it quite high level and quite readable. The main source of documentation for the project is a book that I published with Cambridge University Press called Dense Sphere Packings. This is more than 300 pages. I'll show you the PDF in just a moment. But that's all cross-referenced with the proof scripts inside the project, so you can go. So if you don't want to read the whole light proof scripts, you can go to the book and see, in more mathematical language what it's saying. Jacques was so kind to line up a lecture in Edinburgh in 2002, Lessons Learned from the Formal Proof of the Kepler Conjecture, and this was recorded, and it seems to be the source that most people go to now to learn about the Flyspeck project. So if you want a 1-hour YouTube overview, I suggest that. And then Soloviev, I'll mention him several times today. He was the person most responsible for the formal verification of the computer program parts of the proof in his thesis, and you can find his papers at his website at the University of Utah. There's an old proof of the Kepler conjecture, the original published proof from 1998. Don't buy the book because it's all available at the archive. This is why I don't make a book plug. So let me just show you a couple of these things. So this is the Forum of Mathematics. And if you go there, you find, if you go to the most read papers for trending right now, number one, these are all the collaborators on the paper. So you have access to it there. This is Alexei Soloviev that I just mentioned. The picture is a little small here. This is Huanglei Trung. He was our chief formalizer, so he did large parts of the text part of the proof. This is Tati Hoi An. She was our first project manager in Hanoi. So I sort of showed up in Hanoi not knowing who to talk to or who to get help from. And she really got things organized, a lot of people involved in the project, and really made things happen. So she was really critical for the project. Here's the GitHub page. You see, for instance, you can get a link here to the book Dense Sphere Packings, which is all the documentation. And it's roughly organized. This text formalization directory contains the book and all the text parts of the proof and the proof scripts for that. And then, as I'll be describing in further detail, there are three main computer programs that need formalization, and those are the formal graph, formal inequalities, and formal LP subdirectories of the project. And we have some informal code. Downloads contains just PDFs of different projects. So I'll go back to my slides now. So the Kepler conjecture that I'll be talking about, it's a simple assertion that no packing of spheres in 3 dimensions has density greater than the familiar cannonball arrangement with face-centered cubic packing, and its density is pi over √18. And just as a basic picture to keep in mind, as sort of the text part of the proof. And then there's some part computer program dealing with planar graphs. There's a part dealing with linear programs, and a part dealing with verification of nonlinear inequalities. And so those are the basic 4 pieces. The text sort of shows how these pieces all link up. So I'm not going to go into details about proof, but I just want to give one slide to give enough background so that what I say makes sense. So what you do, so you start with some packing, filling all of space in 3 dimensions. And then the first step is to reduce from a statement about an infinite number of spheres to a finite clusters of spheres. You want something that you can handle by computer ultimately. And so these are clusters. Eventually you reduce to clusters with at most 15 spheres around one in the center. And what you do is you have a rule, so you want to discretize this. So you have a finite number of combinatorial structures that you need to consider. And what you do is you just connect the centers of the spheres if they're sufficiently close together, and then you project those edges down to a unit sphere in the center. And under suitable hypotheses, you can prove that this is then a planar graph on the surface of this sphere. And then you view that just purely combinatorially, and the question, so you want to encode any potential counterexample as a planar graph in this way. And then it's a case-by-case argument that rules out each potential counterexample one by one by going through the list of graphs. And for each graph, you have a nonlinear optimization problem that you need to bound the maximum of some nonlinear function. That's hard to do in general, but we take linear relaxations of those nonlinear problems, and there are efficient ways to do linear programming, and then you solve those linear programs and show that in every case you do not have a counterexample. So once you've ruled out all possible counterexamples, QED, you're done. The face-centered cubic packing has the best. Okay, so just in one slide, that's the sketch of the proof. And you see here in one slide why planar graphs might be coming in, and nonlinear inequalities might be coming in, and why linear programs might be coming in. Any questions?
How many spheres are touching the central sphere in the face center cube?
So you have 12 spheres touching every other sphere in the face center cubic. Yes.
How many counts?
So I'll say, I've got a slide that gives the exact number, but it's about 18,000.
18,000.
Okay, so I'll start out talking about the text part of the proof. The first step is, okay, so I just threw up this sentence at the beginning here. Each day we ask how to formalize the proof most efficiently. I simplify the proof by writing whole line scripts. And it turns out that, so this was the question I asked myself every day in doing the formalization. And most days the answer was to simplify the proof rather than creating new proof scripts. So this is partly because of my background as a mathematician, but an incredible amount of work went into transforming the proof from something that referees were unable to check into something that a computer was able to check. So roughly speaking, different decompositions of space lead to different ways of bounding the density of sphere packings. I won't go through all of these different decompositions, but there's you have a bunch of sphere centers. If you take the perpendicular bisectors, you get what's called the Voronoi decomposition. If you take the dual decomposition, you get what's called the Delaunay triangulation. And early approaches were based both on Voronoi cells. So Feshtot was the first person to have a very concrete strategy about how to give a proof, and it was based on Voronoi cells, but it was really computationally infeasible. So I sort of gave the dual construction in the early 90s. That, again, ran into problems. And the first proof in 1998 was based on a hybrid decomposition that switches back and forth between Voronoi cells and Delaunay decompositions, depending on what the needs are in given different regions of space. Then in 2007, Marshall wrote an article proposing a variant of what we had done, and the rules for the decomposition of space were really much cleaner than what we gave in the 1998 proof. And this was a big improvement. And in the second, so we have a second generation proof that was used for the formalization. And in that, we switched from one decomposition of space to another, the second one based on this decomposition given by Marshall. So the Flyspeck project, 2007 to 2014, when the project was completed, uses this new decomposition of space. And then John Harrison was the author of Light, was very much involved in this project, and he developed libraries to support the project, including measured integration, including the gauge integral of Fubini's theorem and so forth, affine and convex sets, topology, theory of polytopes, and so forth. So that's all I'll say about the text part of the proof. Let me just show you the book. So if you go into the book, you see every lemma is labeled with random codes. And then if you look inside the proof scripts, we've got the same random code going with the lemma. So these are our tracking codes to correlate what happens in the text with what happens in the code. So you can just grep for this number and find everything in the project that uses the lemma or proves it. And then you can just check. So the book was written at the same time the formalization was being done. We were editing it, so if something wasn't working, we edited the book. So it's not like a lot of formal proof projects where you have some book that you're formalizing and then you find all the mistakes in the book, but the mistakes are still there in the book when you're done. Here it was more an interactive thing, so as mistakes were found, we corrected the book and then we kept it in sync with the project.
Has this book been read by the referees of the initial paper?
The original referees, I don't know that they've read the book. The chief referee for the original proof was Jeff Ligarius in the end. And a lot of referees that gave up, but he's the one who took it to the end. And he wrote a review of this book for the Bulletin of the American Math Society.
It's positive.
And it's positive, except he still treated the theorem as unproved.
So this was after all.
It was after Flyspeck was done, and he still, since the paper had not been published, he still would not.
Still a conjecture.
Still a conjecture.
So the question was whether.
So how is it ensured that the documentation in the book is mathematically equivalent to the formal code?
I mean, there are some subtle differences between the two, but it's just, it was just me checking that the two were in line, and in the end, we did get a formal proof out of it, so we hope that what's in the book is
So
not
the
too
formal proof
inaccurate.
proved something, and you believe that's equivalent to what
Yes.
what is in the book.
But there have been a few errors reported in the book, so it wasn't perfect. Yes.
Would you say that the proofs that are described in the blueprint are also very much alike the ones that are formalized?
Yes, so I wrote the proofs. I tried to make everything quite modular so that different people could work on different chapters of the book without it interfering. I tried really hard to design things in a way that it would.
My question was more on the actual content of the proofs. I mean, so the statements are.
Yes.
But also
There are a few departures, but it's quite close.
And so the part where there are these thousands of examples to be checked,
Yes,
I guess that's not in the book, right? Or is,
that's not in the book. So there's some, the book has, so if you download the PDF from the Flyspeck project, there's some long appendices that are not part of the published book that describe how the computer code links up with the text part. That's in the PDF, but not in the published part. Okay, so let me talk about the nonlinear inequalities. There are about 1,000 nonlinear inequalities. I'll show you a few in a moment. That are automatically formally verified. This is the longest computational part of the proof. This takes about 6,000 hours on a cloud computation. These inequalities have been now verified by 3 different groups. Sloviev did it originally in an Azure cloud computation. Then Joseph rechecked those calculations, and then the referees for the paper also went through a check of these inequalities. So many of the inequalities are automatically generated and specified. You have a question?
Yes. So about how general is this the part that verifies nonlinear inequalities? Is it sort of the same machinery that with just sound inputs, or do you need a separate, different way of verifying each inequality?
They're all verified by a uniform method based on. So I've got my next slide goes into a little more detail, so I'll discuss it on the next slide. You don't want to try to formally verify false inequalities, and so we subject these inequalities to a variety of tests before attempting the formalization. This includes running them through nonlinear optimization software to check the inequalities, and then actually doing a C++ interval arithmetic based rigorous mathematical verification, but not a formal verification of each inequality before we actually try to do it formally. And then
Is that much faster than the 6,000 hours?
yeah, so it's about 10 hours just in C++, and then we have a slowdown factor of about 600. That was really good. We were very happy. It was only 600 times faster. The original estimates were about 10,000 times slower. And with work, we got it down to 600. We needed to chop these inequalities up into smaller pieces to be distributed out on the cloud computations. On the end, there are about 23,000 subproblems that got found out. So we used a compiled version of whole light. Usually it's just interpretive, we needed the speed. All computations are done internally in whole light, so that means no native floating point arithmetic is used. It's all implemented in the logic. So this was a large part of Solovyev's thesis. He developed arbitrary base arithmetic, floating point, interval arithmetic, multivariate Taylor series with their estimates, automatic differentiation, adaptive subdivision algorithms, and so forth. And all of this was formalized inside whole light and automated so that you can just write down an inequality, and then it gets shipped off and it automatically computes and verifies all the derivatives and proves Taylor expansion theorem with error estimates, and then uses that with verified floating point and interval arithmetic to prove the inequalities. So these are low precision computations. People often ask, we use special algorithms for high precision arithmetic, like fast Fourier transform algorithms for multiplication. And that's really not necessary at all. These are not high precision calculations. You just have to verify everything you do. So many of them might not use more than 4 or 5 decimal places of accuracy. And one of the things Soloviev did is that he pre-computes exactly how many decimals of accuracy you need before doing it formally, so that you're really using the minimum precision necessary. Yes?
Do you happen to know whether whole light offered symbolic binary arithmetic prior to this?
Yeah, so John Harrison has a very nice binary arithmetic library.
So he built on that.
So the thing that Soloviev added was arbitrary base, because the arithmetic is very slow inside whole light. And so what you do is you build up, you work with a large base and build up a large multiplication table, or as much as you can store in memory. And then you just look up all the multiplications when you do the actual.
Symbolically.
Yes?
Amazing.
Okay, and then the way whole light is designed, you're not allowed, it's not parallelized, right? You're not allowed to import theorems from another session. We had this big cloud computation, so we had to create a specially modified kernel that did allow for the import of statements proved in another session, so that we had one master session that verified that none of the pieces were left out. And so we used that special version of whole light just for this one calculation to make sure that all of the pieces from the cloud computation fit together. Okay, the linear programming proof. So this is the PhD work of Stephen Oboa and Soloviev finished this off. There are 43,078 linear programs that need to be certified as part of the Flyspeck project. So the rough size is just very approximate, because there's quite a big variation in the size of the linear programs, but you should think of them roughly as involving about 1,000 variables and 1,000 inequalities each. And a lot of the inequalities are sparse, but we're able to use a sparse matrix representation for the inequalities. So just to say a word about how linear inequalities are dealt with. So if you have a maximization problem, say maximize Cx such that Ax is less than or equal to B and X bigger or equal to 0. So you should interpret these all as vector quantities. So A is a matrix and C and X is the dot product of vectors and so forth. You could say that Cx, you want to give an upper bound on the maximum, and using that X is positive, you can say that C is at most AY if you add the condition C is at most 1 A, where Y is going to be our linear programming certificate. And then AX is less than or equal to B, and so if Y is also greater or equal to 0, then this is less than Y B. So any vector Y that satisfies this inequality and has non-negative entries will be an upper bound on this linear program, okay, just by these easy inequalities. And then linear programming dualities, as if both problems are feasible and bounded, then you actually get equality if you pick the best possible one. So we want to bound a lot of linear programs, and what you do.
ABC integers? ABC
No,
integers?
these are, so we use floating point there. So what we do is we use untrusted software to do computations, GLPK, in floating point to get approximate values for the certificates Y. And then we sort of send it through a sanitizer. You know, we replace all the negative entries by entry 0, and under pretty general sort of bounded conditions, we can force Y to to satisfy this inequality. And we might lose some epsilon in the process when we clean up the certificate, but we're able to get some upper bound on each of the linear programs. And so then we use the untrusted software to compute the certificates for these 43,000 linear programs. When they get cleaned up, we import them into whole light and then just check that these inequalities hold so that we have an actual certificate of an upper bound on each linear program. Yes?
How much would it save to inline certificates? Like how much?
Inline, you mean actually compute them?
Just yeah, figure them out beforehand and then put them in proof.
That's what we do. That's what we do, yeah. So this you only need to compute once, and so this was, Sloviev computed these just using a C# program and hooking it up to GLPK. Those are all stored at the Flyspeck project page, and then when we do the proof, we just replay certificates.
How do you go from the linear inequalities to the nonlinear inequalities?
Yeah, okay, so this is a complicated story, but so the basic idea is that anything in high dimensions needs to be done with linear inequalities, and things in low dimensions can be done with nonlinear inequalities. So we try to find the nonlinear inequalities to about at most 6 variables or so. So we have these graphs, and we're proving some nonlinear optimization problem associated with the graph. Each nonlinear inequality, it can't involve all of the spheres and edges and everything because that would be too high a dimension. So we'll just pick out something like one tetrahedron inside this picture. And a tetrahedron is just 6-dimensional, determined by its 6 edges. And we have edges and other quantities of interest like dihedral angles and volumes and solid angles and everything. And so what we write down are inequalities in 6 variables that relate the edge lengths to solid angles, the edge lengths to volumes, the edge lengths to dihedral angles, and so forth. And that gives linear approximations to what the dihedral angles are and so forth. And then all of that information is fed into the program. But the key is to keep those inequalities in very small dimension, make them easy to verify.
Can you show an example of
Yeah.
a nonlinear inequality that needs to be verified?
Okay, so here's an example. So the first part, okay, so this is giving for all something. Then this is a 6-dimensional inequality. The bounds on the variables all run between 2 and the square root of 8. So draw some cube. And then the main part of the inequality is this function delta, which is a polynomial in 6 variables, is strictly positive, and the circumradius is less than square root of 2, implies that some other function of 6 variables is greater than or equal.
So these are polynomial inequalities? Everything? No.
So the inequalities are all generated from field operations, square roots, trig, and inverse trig functions. Okay, so the file.
Wait a moment. Ah, that's whole light code to generate whole light formulas, yeah.
So this is, so the way whole light works is everything's OCaml code except what's between back quotes. And things between back quotes are the precise mathematical terms in whole light. So this is just a OCaml structure. And then we have various tags about it. So this is information about how to export it to C++ for verification, how to export it to nonlinear optimization software for verification. And these tags sort of set all the parameters that we need to generate C++ code. And like this one says sharp. There are just a few inequalities where you actually get
There's one point where it's equal.
one point where you have equality, and those are a little bit tricky to verify. Most are strict, and so you have some epsilon you can play with. And it's just a file that goes on, hundreds and hundreds of inequalities.
So most of these formulas have been generated.
A lot of them have been automatically generated.
Wondering why one is there. Syntactically a bound variable. Sorry, it's a
Why?
very low level comment. So like why one, that is a list, and that is a whole light list. Is that
Yes.
actually a bound variable somehow?
Well, I've got this all for all at the top that's automatically binding all of the.
But somehow processes that thing and binds those variables. Wow.
Okay, so the way to read this is that an inequality gives the domain as a list of variables and ranges, and then equality that has to hold.
But it's a whole light value, which is then somehow turned into a quantified formula.
And how do you get these 1,000 linear variables from these few non-linear variables?
Well, some of them are just slack variables and things, so they don't need it.
Okay.
But what you do is you have, say, an inequality that holds a relation between its edge lengths and, say, dihedral angles. And then you can apply that inequality to every tetrahedron in.
Yes, but this makes 6 times 15 or something.
Yeah, so.
This just makes a few hundred and more.
Yeah, okay, so 1,000's an upper bound. So there are more constraints than inequalities in general. Okay, so back to linear programs. We generate the dual certificates, as I just explained, in GLPK, and then import into whole light. SlowDev worked a lot on the optimization of this procedure. It's really quite fast, so maybe a second or two to do linear program of this size. So linear programming is a big success story, right? It's now possible to do problems with millions of variables and so forth. So These are very small mini programs by standards of what can be done. Planar graph generation. In the original 1998 proof, there were 2,771 graphs. We had a collection of about 5,000 graphs, because as we were developing the proof, any graph that was ever found in any version of the software was just left in for testing, and then when Nipkow and Bauer did the verification, they found out that only 2,771 were actually necessary for the proof. In the our second generation proof, the Flyspeck version of the proof, there are 18,762 graphs. You might ask, why do things get so much more difficult in second generation proof? Shouldn't things be getting easier? The reason is that this was the first part of the project that was completed, and this was working. And so I just pushed more work in that direction. You know, you can sort of decide how you divide up the different parts of the project, and you give more work to whatever is working, and reduce the work of what's not working. So in the end, there were a lot more graphs. So this part was done in Isabel. This is the most unsatisfactory part of the proof, of the formalizations that we have. These two different proof assistants involved. The Isabel project, so in the original proof that we completed in 1998, we used Java to do all the graph generation, and this was done by I started out doing this all by hand, and then I got too complicated and I put it into the computer. First did mathematics, and then Java. I would just start by drawing pictures. You know, I wanted a planar graph, so I'd draw a polygon, and then I would start adding on different faces and so forth. And this became the Java algorithm of drawing a polygon and then adding things to it in such a way that you don't cross. And then in this Isabel project, you don't want all planar graphs. You only want the planar graphs that are potentially counterexamples to the proof. And you give a list of combinatorial properties that any counterexample has to have. And those combinatorial properties are summarized in the notion of a tame graph. So this is just a purely technical term used inside our proof to mean exactly the long list of properties that a graph has to have to be a potential counterexample to the Kepler conjecture. So you give bounds on the number of vertices it can have, on the degrees it can have, and size of the faces, and so forth. And so this part of the program is you want to start out with arbitrary planar graphs, and then filter out all of those that aren't tame, and then what you're left with is a list of tame graphs. So conceptually, it's easier to think of it as generating all planar graphs and then getting rid of those that are not tame. But when you actually write the code, you want to be throwing away graphs as you generate them rather than generate all planar graphs. And so that's what this project does. It proves all these lemmas justifying that you can throw away different graphs at various stages of completing them, and you never throw away anything that you shouldn't. So they take, in the Isabel proof, they take this part of the generation of planar graphs just sort of as a black box. I have this piece of Java code that generates planar graphs, and that becomes the definition of what a planar graph is. Anything generated by the Java code or its translation. No, this is the definition of planar graph.
Okay.
The definition of planar graph is anything generated by this algorithm, by the Java code or its translation in general. So this turned out to be, and then they take it from there and then filter out and show the changes conditions. So this turned out to be a mistake because then we translate what they did into whole light. So by then we have a double translation, starting from, well, Java to ML to Isabel to whole light. And by that time, this algorithm for plain graph generation was almost completely unusable. Or very difficult to prove anything about it, right? It's just treated as a black box in Isabel, and then on the whole light side, you have to prove that it connects up. So on the whole light side, we were using, based on what Gaultier did with the four color theorem, we were using hypermap representations of planar graphs. And so there was a unpleasant thing that we had to prove that, this, double, triple translation of this old piece of Java code actually correctly matches up with the hypermap definition of planarity. Okay, so I think I've gone over the main pieces of the proof. Glad to answer any other questions.
Do you remember how long does the latest running of the Isabel extracted code for the tape classification? Like 10 hours or something?
That's roughly correct.
Wondering if the blow-up factor would be the same as for the C++ code.
No, not at all. So, according to Soloviev, graph processing or list processing in whole light is almost as fast as list processing in objective camo.
Yeah, but I mean, like even.
So we should be able to. So in the Isabel proof, this was done using reflection and the calculation was exported. But I think if somebody puts it in whole light, it should terminate within a reasonable time.
Do you have any idea how the mathematical community as a whole feels about this particular proof and maybe more generally about proofs using such methods? But your referee doesn't accept this, you mentioned.
Well, now that it's been published, I think he should accept it. He was waiting for the referees. But I think the proof is fully accepted now by the mathematical community.
Do they raise issues like maybe there's a bug in your camel, maybe there's a bug in whole light? Did the reviewers raise issues like that?
I mean, our paper discusses these issues a bit, so we force the referees to be aware of these issues. But they didn't bring up anything that we didn't point out already.
But is it clear to you where the bar is? Suppose that you have users Mathematica that is huge, maybe they don't trust it. Do you think they would accept the proof if you have users like a big piece of computer algebra system that's doing a lot of computations that
Do mathematicians accept something like
Yeah, just stay
mathematics?
with you. I mean, if you have uses Mathematica in your projects, as a shortcut,
Yeah, so the original 1998 proof used Mathematica a great deal. For instance, we used it to generate all of the linear programs. The linear programs were done outside, but to manage the workflow, we used Mathematica. There's a huge range of opinion in the mathematical community. Some people really understand how things work, and some people do.
And it also depends on which field in mathematics. So in number theory, people are probably much more critical to using computer-assisted methods than in real analysis, where it's much more common and has a long tradition to use computer-assisted proofs that are just based on interval arithmetic, and you trust the computer. You don't do formal verification. And it's accepted, it gets published, and as long as you give enough details.
Okay, Mario then.
So the final statement of the theorem involves an existence, I think, in this fudge factor.
Yes.
Is that an effective bound? Like, do you have?
Yes, I'll show you the statement. This is our paper. So this is the actual, so here's the definition of packing. We identify the balls or the spheres with their centers, and we make the radius 1. So to say that the balls don't overlap is just saying that their centers have distance at least 2 from each other. And then the statement is saying for every packing V, there exists, so this is what you're asking, there exists a constant. So this is in whole light notation, all ASCII. So this is for all, this is, there exists a constant such that since the radius is bigger than 1, if you count the number of points of the packing inside some big ball, it's at most pi over the square root of 18 is the number that comes up in the Kepler conjecture. That's 74% density. R to the power 3 plus an error term of size r squared, and then as you let the size of the ball go to infinity, this term goes to 0. We divide out by the 1. So the question is, can you be explicit about what this C is? And yeah, it's, a number of people don't like that constant C. I just couldn't be bothered to work it. It's some small, like 10 or something, right? It can be worked out explicitly, but I haven't been bothered to, and it's independent of the packing. So here, the way it's stated, it says for every packing V, there exists a C, so the constant C is depending on the packing. But again, that was just me being lazy. It's just some small uniform constant.
So can you give the breakdown of what parts of the proof were manual checking of the mathematical arguments, what were kind of checking of the algorithmics, and what was just fully automated?
In the formalization, or are you talking about the referees checking?
No,
what we did. So the computer code parts were all fully automated in the system. Nonlinear programs just get shipped off to this tool that proves nonlinear inequalities, and they all come back certified. And same with the linear programs. The graph generation, there are a bunch of lemmas that you need to prove to show that various filtering operations that you do here respect the tameness conditions. So those are done individually by hand. And then the text part, the 300-page book or whatever, that was all just done by people writing proof scripts.
And this is what the folks in Vietnam were up
Um,
to.
Yeah, so for part of that, we just divide up the chapters, different groups.
I'm curious, what's the state of those proof scripts now? Are they because they're all done by different people, so at one point I think there was a bit of work to refactor and improve those, but did that sort of homogenize them, or is that even of interest?
There are different styles that get used in proof scripts. The biggest stylistic difference is with, Soloviev spent a summer internship with Gomser working on Frank Thompson proof. And he came back and implemented SS Reflect in Light and imported a bunch of cock libraries into Light. And so that's quite a big style change from what normally gets done.
Sorry, just one follow-up on that. Do you think those proofs would be understandable as just looking at the full text, or not looking at the book? Or is it not of interest to understand those because?
Yeah, this question is for war. I mean, I don't find her light so unreadable as some others.
So readable or so unreadable?
So unreadable, I don't find it.
I think you get accustomed to everything.
I wanted to understand where is the philosophical divide in the mathematics community about this kind of proofs. I mean the following. One possibility could be that there are mathematicians who would hope for the proofs of this kind of problems to be entirely human. So they're like waiting for a human to come up with some kind of abstraction of new theory or whatever that allows an individual or a team of individuals to conquer this kind of problems without machines. And on the other hand, there are the mathematicians who accept the human-machine interaction as a way to do these proofs. This is a possible divide. I have no idea whether this is the one that occurs. Or else it could be that the philosophical divide is that all mathematicians accept that proofs of this kind of problems be done by human plus machine, but there are divisions on how to do it. So, for example, how many proof assistants, whether should be all symbolic or partially numeric or partially symbolic, whether all the proof assistants should be proved sound beforehand, whatever. But I just wanted to understand where is the divide, because somehow there was a question by Larry on this, and then a comment by you. It appeared you said in analysis is one thing, in number theory is another, but I wanted to understand where is the division. Is there anyone who still dreams that this kind of proofs could be done in simply manual ways, or no?
Yeah, I think there are mathematicians who try to eliminate computer proofs whenever they can. We've seen that with the classification of finite simple groups, for instance. People work to eliminate the computers from the work that was done on sporadic groups and so forth. But that's just one point of view.
So they are both, probably.
Yeah.
Okay, Larry, one last question and then.
Okay, and the point I made in my talk a couple of weeks ago, I think part of a mathematician's objection to this sort of proof is that something as fundamental as this should be true for a good reason, and a good reason would never require checking thousands of cases. But I think a sideline on this is this cannonball packing, is this the unique optimal packing? Because all you're mentioned here is no packing is better. But if there could still be many packings that equal the cannonball packing in terms of density, then you have a much more complicated situation than if this cannonball packing is the one unique one that achieves the maximum density. And then maybe you would expect a simpler reason why it is the case.
It's not unique.
There are uncountably many.
Oh dear.
So I have a question related to what Gary said, you know. So what about Ryan's proof of the Fermat's last theorem? That's also very complicated.
What is the question?
No, I'm asking, like Larry said, this thing, one of the reasons why mathematicians don't believe or may not believe, may question the proof that Tom came up with or others. You know, Fermat's last theorem's proof is also very, very complicated. That many people in the world don't understand it.
Oh, but it's not just a huge case analysis.
Okay, this looks like something we need to discuss over here. So let's, thank Tom.